Welcome to This Explainer. Today, we're diving into one of the absolute biggest challenges of our time, the transition to a fully renewable global power grid. Now, we all know wind and solar are the future, right? But actually building a power plant that can completely replace fossil fuels, that requires an incredibly rigorous scientific approach. So we're going to embark on a deep dive into a complex, multidimensional, but honestly thoroughly fascinating scientific framework. It's known as the 6E analysis. By the time we wrap up here, you're going to see exactly how engineers and scientists rigorously stress test a hybrid wind-solar power plant to guarantee it can actually keep our lights on for decades to come. Okay, let's dive into this. Here is our roadmap to help us navigate all this without getting lost in the weeds. We'll start with the renewable energy challenge, move into the hybrid power solution, explore the 6E analysis framework, dig into thermodynamics, specifically energy and exergy, look at the economics and environment, and finally, deliver the final verdict. Starting right off with Section 1, the renewable energy challenge, or as I like to think of it, the unpredictable nature of nature. I want you to really think about this for a second. What actually happens to the power grid when the sun isn't shining and the wind just isn't blowing? It sounds like a super simple question, but it hits on the absolute core vulnerability of a standalone green energy grid. You and I demand electricity 24 hours a day, 7 days a week. But nature? Well, nature definitely doesn't work on our schedule. In the scientific community, wind and solar are actually referred to as stochastic renewables. That's really just a fancy word meaning they fluctuate wildly based on totally unpredictable weather patterns. Relying entirely on just a standalone wind farm or just a standalone solar farm creates some pretty dangerous power fluctuations. It means sometimes you have way too much power, and sometimes you literally have none at all. And for the grid operators trying to keep our everyday electricity running smoothly, that is a total nightmare. So, Section 2, the hybrid power solution, combining forces for stability. The sheer elegance of this solution is how it physically comes together. Instead of building a wind farm way over here and a solar farm way over there, we merge them. We put them into a single unified power plant. The wind and solar inputs combined at a central point before ever going out to the grid. And because wind often blows strongest at night, or during completely different seasons than peak sunlight, the two sources naturally complement each other. It's brilliant. It creates a much smoother, way more reliable output of electricity to the load and the wider grid. But of course, you can't just build a massive infrastructure project like this and just cross your fingers, right? You need data. The study we're exploring today modeled a 5.6 megawatt hybrid plant, half wind, half solar, located on the coast of Gujarat, India. And they didn't just guess how the weather would behave based on last year's forecast. No way. They used 41 years of high-resolution climate data, going all the way from 1979 to 2019. Using over 4 decades of data guarantees highly accurate long-term predictions about power generation over the entire multi-decade lifespan of the project. It completely removes the guesswork. Which brings us to Section 3, the 6E analysis framework. 6 lenses to evaluate power. To truly evaluate if a power plant is viable, scientists need way more than just a basic cost analysis. This is where the 6E analysis tree comes in. Think of these as 6 distinct lenses that let us ruthlessly scrutinize the hybrid system's true worth. First, we have the thermodynamic branch, which covers energy, exergy, and advanced exergy. Then we have the economic branch, the environmental branch, and finally, extended exergy, which actually blends economics and exergy together. By looking through all 6 of these lenses, developers can pinpoint exactly how well a system performs, where it wastes energy, and how much it will really cost. Let's dig a little deeper into that first branch. Section 4, Thermodynamics, Energy and Exergy, finding the useful energy. Okay, we have to demystify some heavy jargon right out of the gate here. You've definitely heard of energy, but what on earth is exergy? Well, the first law of thermodynamics says energy is always conserved. It never just disappears. But the second law tells us that the quality of that energy degrades over time. Exergy is the useful portion of energy that is actually available to do real work in our system. It's the stuff we actually care about. It represents the real-world electricity we can use before it gets lost as just useless waste heat or friction. By tracking exergy, engineers can figure out exactly where a system is underperforming. And scientists don't just measure that waste, they meticulously categorize it. They split exergy destruction into endogenous, meaning losses caused by the component itself, and exogenous, meaning losses caused by other components in the system messing it up. Then, crucially, they split it again into avoidable and unavoidable waste. Why does this matter so much? Because it tells engineers exactly what can be fixed with better tech, the avoidable parts, and what is just a strict law of physics that we just have to accept. Let's compare how this useful energy gets destroyed in solar panels versus wind turbines to really see this in action. With solar, a lot of exergy destruction is unavoidable, just due to the basic physics of solar radiation hitting a panel. But there is an avoidable portion. We can fix that by developing better panel materials that don't lose efficiency as they heat up in the sun. Wind turbines, on the other hand, fascinatingly, they have zero exogenous destruction. A wind turbine operates entirely independently. There's no other component in the plant dragging down its efficiency. Understanding these very distinct losses is precisely how engineers learn to build better, more efficient hybrid systems. Section 5. Economics and Environment. The cost and the carbon. Once you've proven the physics actually work, you have to answer the two biggest questions for policymakers and consumers. How much does this cost? And does it actually help the planet? From an economic standpoint, the study uses a metric called the levelized cost of electricity, or LCOE. Simply put, this is the average minimum price the plant needs to sell its electricity for just to break even over its lifetime. But here is the kicker. The analysis also factors in government policies, specifically things like accelerated depreciation, which lets developers write off a huge chunk of their loan in the very first year. By plugging this into their exergoeconomic model, the data absolutely proves that hybrid systems make excellent financial sense. They lower overall system costs and make the energy substantially cheaper to produce. Now, on the environmental side, the most crucial takeaway is this massive number, 1,407 tons per kilowatt. This represents the specific emission reduction achieved by the hybrid system. By building this hybrid plant instead of a traditional fossil fuel plant, it prevents a staggering amount of CO2 from entering our atmosphere every single year, per unit of capacity. When we compare these setups directly, you'll see the standalone wind system reduces emissions by 1,128 tons, and standalone solar reduces them by 1,685 tons. The hybrid system? It actually sits right in the middle at 1,407 tons. Now you might be wondering, wait, why isn't the hybrid the highest? It's because the hybrid system utilizes shared infrastructure and balances the two sources. So while it sits in the middle for strict emissions reduction per kilowatt, its ability to run steadily year-round provides a much more optimized, highly reliable environmental benefit to the actual grid. Finally, Section 6, the final verdict, the power of synergy. We've looked at the physics, the money, and the environment. When we bring all 6 lenses together, does this hybrid system actually pass the ultimate stress test? Let's look at the performance metrics. We focus on 2 main areas: capacity factor, which is how often the plant runs at its maximum potential, and exergy efficiency, which we now know is how well it utilizes useful energy. By combining wind and solar, the system mathematically boosts its capacity factor by 3.46%, and it boosts its exergy efficiency by an incredibly impressive 5.12% compared to running these systems separately. Let's really hammer these enhancements home for a second. We get a 3.46% capacity factor boost, a 5.12% exergy efficiency boost, and a 2.87% extended exergy efficiency boost, which includes all those economic factors we talked about. Now, to a layperson, 3 or 5% might sound small, but I want to remind you that on the scale of a multi-megawatt global power grid, these precise percentages are absolutely massive. They translate directly into a more stable grid, cheaper electricity bills for us as consumers, and a way faster path to net zero emissions. The researchers summarized their monumental 41-year data analysis with this definitive statement: hybridization leads to superior year-round system performance with smaller power fluctuations than the standalone systems. This is the ultimate so what of this entire explainer. The comprehensive 6E analysis unequivocally proves that the hybrid approach isn't just some neat idea on paper. It is vastly superior to our traditional ways of building green energy infrastructure. Which leaves us with this final thought. How will comprehensive 6E analyses dictate the commercialization of global power grids in the near future? We now know for sure that mapping every single thermodynamic and economic detail, identifying literally every bit of avoidable waste, and optimizing every single dollar is the true key to unlocking a renewable energy future. Thank you so much for joining me on this explainer. I hope you leave today with a much clearer picture of exactly how our green future is being engineered, one exergy equation at a time.